It's like on a, okay. All right, so 5-3. So we did, okay, so what did we do so far? We did the rectangular approximation methods to estimate the area under the curves. We did the trapezoidal approximation to estimate the area under the curve. And we used area to find, say, like who was down there?
Oh, me, sorry.
Hi, Liz.
Or show me just now.
Okay, everyone's here, okay, except for the people that were,
Naughty time, mystery time.
okay, so, and then we evaluated the integrals using area. And we actually had to know whether it was a semicircle, triangle, and then use the formulas. So we're gonna look at rules for definite integrals, and then I'm gonna jump to chapter 6 to get the rules for indefinite integrals. So definite just means that you have, it's got a finite area under the curve. Okay, so you can actually find the solution. So I wanna look at a few of these rules first. We talked about what all the symbols mean in the last class. Do we remember? Like, for example,
Oh, the big
like,
S to the south.
yeah, so like A and B are the bounds. And then f of x is what we call the integrand. Because that's the function that we're integrating. And then dx just tells us that's the variable that we're integrating with respect to. Okay. So order of integration. If you notice here it says A is less than B, which is less than C. Okay, so what? C is just constant. These are all just constants. We're just saying that A is the smallest, B is going to be somewhere to the right of A in terms of like on your x-axis, and then C is bigger than that. It's just to be able to look at all the different rules here. So what if A and B are switched around? Okay, so imagine, let's say you had the top number was smaller than the bottom number. So let's say it went from 2 to 1 instead of from 1 to 2. Okay, so our lower bound and upper bounds are switched around. So in this case, we just make it the opposite and then switch the bounds to make the bottom one smaller. Okay.
So,
Go ahead.
how would you, why would it even be like that? Like, why wouldn't it just be this helpless?
So sometimes we have to separate integrals, which you'll see when we look at this additivity, actually the last one.
Okay.
And then there's another place that we'll see this occur when we do fundamental theorem of calculus, where you have to kind of like separate it and then you have to switch one around so that the bottom, the lower bound, is smaller than the upper bound. And when you do that switch, you just put a negative sign in front. So just basically the negative.
Is there like a rule where that?
So basically switch, when you switch the bounds, it becomes negative or opposite of what it started. Okay?
Is there like a rule?
As what a rule?
You said that like it says the rules for definite integrals.
Uh-huh.
So then how can? Oh, never mind. Just kidding.
Are we okay with that? All right, the 0. If the bounds are the same, then we get 0. Okay, if you try to figure out the area under the curve from 1 to 1, there is no area, basically, it's 0. It's like you haven't gone over any interval there. Constant multiple, so if you have a number, this is actually very similar to derivatives. If you have a number in front of the function, you can bring that out front. So the constant multiple can be multiplied on the inside or the outside of the integral, whichever makes it easier for you. Okay? Some indifference. So integrals, it's as if you can distribute the integral sign, so you can do the area under the curve for f of x, and then the area under the curve for g of x, and then add those two results. So it's just like kind of distributing. And then the additivity one says if you have the area under the curve from a to b of a certain curve, and then from b to c, you can add those two together and basically eliminate b as part of the bounds and combine it to make it from a to c.
What if it was?
So these have to be the same now.
Oh, the like.
The top
Okay.
first one and the bottom second one must be the same in order to combine them. Does that make sense? Do you want to see a picture of that, or we're okay with that? Because the next one, we're going to apply those rules. So we don't have an actual function. We know that we have an f of x and an h of x, and we only know what they're equal to. We don't know what the curve looks like or anything, but let's say from -1 to 1, the area under the f of x is equal to 5. And then the area under the curve from 1 to 4 of f of x is equal to -2. And then from -1 to 1 of h of x is equal to 7. Okay, so look at the first one. What do we notice? This is actually the first rule that we looked at. Yeah, the upper bound and lower bounds are switched. So we're going to change this to make it the opposite, and then switch them from 1 to 4, f of x dx. And we get, it's going to be the opposite of -2, which makes it +2. Good? It's just making it the opposite of whatever it's equal to. Notice we use this one. We didn't want the first part.
Does this get really hard, or is it?
It's just kind of switching things around and kind of manipulating the problem. Some of them are not possible, and in that case, you would just write not possible. So you have to pay like close attention. There might be like a trick one in there. Hint, hint. It's not this one though. This one you can do. So how do you think you can rewrite the integral from -1 to 4 of f of x dx? That's the additivity, because I can make that the integral from -1 to 1 of f of x dx, and then from 1 to 4 of f of x dx. Remember how I said if the top one and the next bottom one are the same, you can combine them. If we have the area under the curve from -1 to 1, and then we also have it from 1 to 4, then we can just make it the whole thing. And what do we get? 5 plus -2, and we get 3. Okay, how about the next one? From -1 to 1 of f of x plus h of x. We can break it up into two separate integrals. So I can rewrite this as -1 to 1 of f of x dx and -1 to 1 of h of x dx. So it's going to be what, 5 plus 7?
Is this the trick one?
Let's see, from 0 to 1, what do you think?
We don't have anything.
We don't have the 0. There's
So we don't have a 0. We don't have enough information. We have from -1 to 1, and we have from 1 to 4, but there is nothing that tells us what's going on at 0.
So we can't do this.
Okay, so it's not possible.
So you just write like.
Just no solution, or you can write not possible.
5 and 7.
How about from -2 to 2 of h of x?
It's not.
Do we have any information about from -2 to 2? No, we have, some people might think maybe we can double it since we have from -1 to 1,
It's just silly.
but you can't. That you can only do that if it were symmetrical, but we don't have enough information, so no solution there. How about the next one? This one's kind of like C, except that we have a 3 in front of f of x and a subtraction, so it's just like distributing. So we have,
Is it for just the f of x, or?
right, it's just, this
So
part
it's
is just
3
f of x. So it's -1, so it would be like pulling the 3 out of the first part. And then it's subtracting just the area under the curve of h of x dx. So 3 times 5 minus 7. Okay. Okay,
Yep.
that wasn't too bad. Okay, so this is where I said now we're gonna jump to chapter 6 and look at the formulas from 6.2. It's just the way that the book has you do integrals all in chapter 5 is using your calculator the whole time. But I don't think that's very, might sound nice, but I think it's better to have the practice with the formulas in this chapter. So you'll see on the homework where I made like a little note to use the formulas for 6.2 wherever you can. If you can't use the formula, see if you could do the area under the curve like we did, you know, when we did the semicircle or making triangles, so on.
With that homework, we're not, that's on one.
Oh, I have a worksheet, that's why.
Okay.
But the following homework, because
Yeah.
we're gonna spend a couple days on this.
Got it.
Okay, so here are your formulas. It says big star. Properties of indefinite integrals. So the reason we say that they're indefinite integrals is that think it's kind of like we're working backwards from the derivative. But remember, whenever we would do the derivative of a constant, what do we always get?
0.
0. So if we're
So then
working
what's
backwards,
0?
we don't know what, if any, constant we might have there. C could be 0, it could be 1, it could be 2. So, or it could be any real number. So when we write the formulas for indefinite integrals, you'll always see this plus C after it. Okay, indefinite integrals mean that we don't know the lower and the upper bound. Okay, it's basically formulas, like if I said what's the antiderivative for sine, we should be able to see that's negative cosine, because the derivative of negative cosine is sine. So let's just look at some of these formulas that we have here. First thing, we already talked about the constant multiple can be brought out in front. We talked about this one. That's just review from 5.3, but the next one is the power formula. So remember with derivatives, we would take the exponent to the front, and then we would subtract one?
Yeah.
Okay, so for integrals, we're now going to add 1 to the exponent and divide by that new power. Let's look at a quick example. So let's say we had x to the 4th dx. So we're going to add 1 to the exponent. So that's going to be x to the 5th over 5, and then we say a plus c. Now, you could always
What is that value?
we don't know what c is when
I
it's
mean,
in the,
just like the answer, what does it represent?
so this represents,
Is that the
The
area underneath
anti-
the curve?
right, this represents the area under the curve.
But how is the area under the curve the antiderivative? I don't get that part.
So, okay, it's a little complicated when you're trying to put it all together and we're getting it in little pieces. But just for a minute here, take the if you were to take the derivative of x to the 5th over 5 plus c, what would you get? What would you do? You move the 5 to the front, right? And then the 5's would cancel, become x to the 4th. Derivative of the constant? 0. Would be 0. So you see how we get back what we started with inside.
Oh, how cool.
Yeah.
I'm forgetting, what is the derivative? What is the derivative?
The derivative is the slope of the tangent, okay, at a particular point. The antiderivative is the area under the curve. And so these formulas give us, I know it's like hard to
And then
piece
how
all
are they
together.
related?
It's a lot of information, but just know for right now, and we'll piece it all together in little bits, but for now, think for the antiderivative, we're just working backwards from the derivative. Okay, this is probably the power formula is one of the most important ones that we'll see. Note that you can't do it when n is not equal to -1 because then you would end up dividing by 0. And when that occurs, the antiderivative for u to the -1 du is 1 over u du. Okay? Well, think about what's the derivative for ln
Then
of
how's
x.
that?
It's 1 over x.
Uh,
The reason we have to put it in absolute values, you can't have a natural log of a negative number, so we have to just make sure that it's positive.
Can you give me an example?
So
this second one is just when n equals -1.
This is only for -1. So really the only example I could give you, well, I could put a number on top. Let's say I gave you 4 over x dx. So the 4 is just a coefficient or a constant multiple, so that could just go out in front. So it would look like 4 ln of absolute value of x plus c. That's it. Go ahead.
You said it would be 0, right?
Right, so we don't do the power, when it's a power, anything other than -1, we use this rule above.
Oh, but for.
But if it's -1, we always end up with natural log, yeah.
But there's no n in the second formula.
What's that?
Cause, n is only representing an unknown, but the second formula is known because it's always -1, cause it only goes to
Correct.
-1.
This is always gonna have for, this is only for powers of -1. If it's any other power, you use the above formula.
Should we distribute the 4 to C, or does
It's irrelevant.
Oh.
With the constant for right now, we're just gonna put plus C. If you put plus 4C, there's nothing wrong with that because it's still a constant. But we generally don't do that. You just leave it as plus C. Okay, your trig formulas. So you need to know basically the ones you're gonna see the most often. You'll see cosine, right? Think about what's the derivative of sine? It's cosine, so the antiderivative for cosine is sine. Question? Think that whatever the derivative of this should give us the integrand. So the antiderivative for sine is negative cosine. Does that make sense? Because the derivative of negative cosine would be negative sine, which would give us positive sine. The antiderivative for secant squared is tangent, right? Because what's the derivative for tangent?
Secant square.
Secant square. And I'm going to highlight all these but the first 3 that I talked about, you're going to see those most often, but you may encounter any 6 of.
On the AP test, so they most likely give us the first 3.
They most likely give you the first 3, but they could give you the other ones also. And then exponential. So take a look at the exponential. What's the derivative for e to a power?
E.
E to the power. So the antiderivative is also the same.
Oh, that's nice.
And then here is if we have a base other than e. We won't see that one as often. And I'm actually not gonna, I have never seen an ln on the AP exam where it's no calculator. So I'm not, it's good to maybe have them in your calculators just in case, but normally we don't, I have not seen any of those recently on the AP. I haven't seen them
That
all
one
on the AP
confused
exam.
us.
So I'm just gonna stop with just those last 2.
For the A to the U, why is that different than U to the N?
Because this is for variables in the exponent.
Like, what, can you
So the ones that I was showing you previously, u to the n, that's when
Oh, the power
the
is a
power
number.
is a real number.
Okay, if the power is a
Yeah.
number.
This is for real exponents. Whereas the one down here is for variables in the exponent. Does that make sense now? The difference? Okay. So let's do some practice. Find each indefinite integral. So x squared. Okay, we're going to add 1 to the power and divide by that new power. And then include the plus c because it's indefinite, So we don't have a starting and stopping point. Okay, does that make sense? So that's why that's why we always include the plus C for those. How about 2 cosine? If you're not sure, think, well, what derivative would give you cosine?
Negative sign.
Negative sign or positive sign?
Positive sign.
Positive sign. So it's going to be 2 sine x. Right here. Right here.
I know.
Okay, so when you're doing integrals, it's sometimes helpful with sine and cosine to just remember they're like opposites from what they were
Yeah.
in the derivative. It may help you, I don't know. Or just memorize like the integral for cosine is positive sine, but the integral for sine is negative cosine. Okay, what's the integral for e to the x?
E to the x.
Just e to the x
Plus C, right?
plus c.
Why did you spend so long here?
I don't know. I think
It's saying C.
they're having a discussion over there. I don't know what's going on in the back there. Greg, you all right? Okay. Anybody want to do D? You want to do D?
I think what I
Do you want me to look at it?
Would I simplify that after?
Yeah.
Okay.
Okay, Jackie's going to do D. Did we get it?
He's not making C.
Okay.
He says you
Oh,
can
yeah.
accept it, so
Okay. Let's say you have a curve. You've got to find the area under that curve.
Keep pressing the button.
Let me start with something that you know, like, let's say you have y equals x squared.
Yeah.
And I said, oh, well, what's the area under the curve for x squared?
Okay, there we go.
So,
How do I
x
erase?
squared looks like this, right?
Oh, you don't know where you're coming
We
Great.
don't know where we're starting.
I got it.
You hold down.
No, we don't know where we're stopping. So that's why we call it indefinite.
Sorry, my
interval.
handwriting
It's
is really ugly.
So
What?
our answer
It is, right?
follows
Oh,
this
because it's the
curve. So that's why I said it's a
So
little
if it was
complicated right now.
4x,
We're
what
gonna
would the
get
derivative of
other
that be?
information on slope fields and other
There is one.
things. When the air comes in.
Okay, so is that right? Is that right?
Cause we don't.
We know the original function, but and if we're looking for the area under the curve,
We don't know the derivative.
right? Okay, so if I know the start and stop point, I have a definite answer. But what if I don't know? So I'm gonna get this, it's gonna model the behavior of x to the third over 3 as our solution, but we have this plus c because it doesn't have,
If your model's the behavior, then why, then as x gets bigger, then you just look at the x, so that gets bigger.
right, but we have to make sure that when we take the derivative of this, we get back what we started with. Right?
There's no c.
That's why I said, right, the c goes away.
Constant, so the derivative is 0.
Okay, anybody wanna try E?
I said, no, I get
Yeah.
that.
E?
No, I don't know.
You want me to see it?
Yeah.
Yeah, that's perfect, just plus C.
Oh, yeah.
Everybody got D? And then, somebody wanna try F? F helps if you write square root of x as
Excellent.
x.
Always.
Shelby, you wanna? Maybe. You want me to see it first? Okay, so 3e to the x, and then 2x to the 5th over 5, plus c. Perfect.
That's so cool. It writes so easy.
Isn't it nice?
Yeah, you guys should all get them.
I know, everybody keeps this.
Obsessed with Maya.
Isn't it awesome?
That's so cool.
That looks good, and then x
So then
to
there'd be
the
no
3
C
has.
because it'd be plus C and then
No, it's
minus
still gonna
C.
be plus c.
Is it plus 2C?
It's always plus c.
Not 2C?
Just always plus c. We don't need to have, if you put plus 2c, technically that's,
Well, wouldn't this be plus C2, but then the minus would distribute, so
No.
then
it's all just plus c at the end,
oh, okay.
just at the very end.
So, like
Because we don't
And
know
then-
that these two c's are necessarily equal to each other.
right.
So that's why we can't cancel.
True.
Now rewrite that as
Simplify.
3x squared. And then
Wait, so
minus
you do 3x squared plus c minus 2x.
And then just rewrite that as 2/3. Yeah, perfect. Perfect.
Okay.
And you can just leave it at plus c instead of c.
Wait, you do 2 c's?
Mm.
Or
No, you don't
oh,
need to
I
c.
overheard something
You,
about that.
you don't have to do c after each part. You just automatically put a plus c at the very end.
Oh.
You don't need a coefficient in front of c. When we do differential equations later on, we will work more with the c and figuring out what c is equal to in certain cases. So we get 6x squared over 2. Yeah, and she puts plus c after each one, but again, you don't, that's fine. Just remember at the very end, it should just be a plus c. And this is minus 2/3 x to the 3 halves plus c. Great. Anybody with G?
Could you do C for each one?
I'll do it.
No, just the very end.
I've got one. What?
Uh-oh.
Oh, I tried to scroll down because I'm using a different app.
The one person
There, I scrolled down for you.
You could be an
who has Surface drew
Right through my
on
notes.
different
Because I have it in a Word document.
Yeah, I was used to using a different program.
All right, so just power rule, right? X to the -1 over -1 plus c.
I love that one.
So -1 over x
Mhm.
plus c.
Oh.
Gotta forget that.
You got the plus c. All right, anybody for h?
Yeah, I think this one's mine. Hey, yeah, it is.
I can do it. H? What are these volunteers? So the antiderivative for negative sign,
How do you get, is that?
just press X, yeah. The antiderivative for negative sign is it cosine or
Negative,
cosine?
negative cosine.
Cosine. You had it right.
It's,
You had it right. Well, what's the antiderivative
oh,
for sine?
yeah.
Negative cosine. So if there's a negative already in front, they cancel each other and make it positive. Perfect. Anybody want to try I?
I'll do it.
Here, I'll scroll so you don't have to. Does that make, we're okay?
Once we hit the balance, we start plug in the lower.
Yes,
Okay.
we will get to that point. And
C.
that's why I said this method, and then I'll teach the fundamental theorem of calculus, which is exactly what you're talking about.
Okay.
There's part 1 and part 2 of the fundamental theorem. And it will all come together. Perfect. Everybody agree? Yes, looks great. Okay, last one, 4 square root of x. Anybody? Should I just do it? Okay. So again, maybe just rewriting it as x to the 1/2 first. So it's 4x to the 3/2 over 2/3. Or, sorry,
I did the same thing.
over. Well, I'm so used to just switching it right away. So it's 4 times 2/3 x to the 3/2, so 8/3 x to the 3/2, and then plus c. I'll just put my plus c. And whether you write 8x to the 3/2 all over 3 or just 8/3 out in front, it makes no difference. Okay. All right, we are actually going to pause there.
Perfect.
And I'm going to give you
Just ask for a break.
a worksheet. How convenient.
Yeah.
So this is assignment 38.